So I'll talk about the subject that I'm doing recently. It is something related to the dark matter. And this dark matter is very interesting from different viewpoints. The one I'm particularly interested in is from the viewpoint of particle physics. And the application of particle physics to cosmology is inevitable when we consider the evolution of the cosmological phenomena. But the thing I'm particularly interested in is this so-called dark matter. There are so many speculations about what is dark matter. And from the viewpoint of particle physics, the more likely candidate is neutrino. The one I say that because if you think in terms of the early universe, when the quarks are created and quarks are combined into mesons and baryons, in all these processes, eventually they will decay. And if you look at the particle data in the past decades or so, you find out that all the baryons, the resonance height, those with mass much larger than proton or neutron, you see that all of them decayed. In the final product, they are stable particle. And neutrino is the one which appears in any process when it comes back to the lowest any state or lowest particles. Each channels, there are neutrino there. So by estimate this decay of elementary particles in the final process, you get a feeling that neutrino is very abundant there. But because it has weak interactions, we know that it's very hard to detect in the laboratory, let alone in the universe. So I think it's quite reasonable to say that this neutrino is one of the most abundant particles in the universe. I would say, based on the process that you can see from the particle data, it is as much as the electrons. And when I say neutrino, I'm particularly saying is anti-electron neutrino. These particular pieces is as much as the neutrino, as much as the electron in the universe. And if you look at it, because the universe is electrically neutral, the number of electrons is about the same number of protons. And what is the number of protons in the universe? People estimate this about 10 to the 80th power. It's a very large number. Based on this phenomena, I come to the conclusion that it is most reasonable to investigate what is the role played by the neutrino in dark matter. And the conventional viewpoint of the dark matter assumes that the dark matter has only gravitational interactions. And because it has only gravitational interactions, so far, it's very hard to find a candidate which actually has some connection to what we observed. It's just very hard. So there are all kind of speculation about the WIMPs or any other type of particles. They are not observed. The only thing which we know, neutrino is always there, and it must be produced by all calculated process. So I'm thinking that what can the role neutrino play? If you are thinking neutrino use the gravitational force to affect the rotation curve in the spiral galaxies, it sounds unlikely. But fortunately, if you look at the established particle physics, there are kind of gauge symmetry, there are conservation law of all kind of charge. We have a conservation law of chiral charge of quarks, conservation law of electric charge. We also have the conservation law of lepton charge or quantum number, or baryon charge or baryon number. So look at this. These conservation law, according to the viewpoint of gauge symmetry, they must be associated with some kind of gauge field and some kind of force. But since the force has never been detected in laboratory. So people always say that, not always, either these force will be small. I'm talking about the force or the Leptonian force. They have a charge there. We know it is conserved. But either they are coupling strength or the charge is very, very weak, or it does not exist. I use assumption that based on the particle physics with the symmetry principle, I assume that it exists, but just very weak. So I'm able to argue that if we assume the number of neutrinos, I'm particularly talking about high electron neutrino, okay? If this number, this kind of neutrino is as many as electrons, then we can estimate what kind of coupling constant, how big is this Leptonian charge in order to produce the observed effect of dark matter on the rotation curve in a spiral galaxies. And I'm able to estimate that this is a roughly automagnetic estimate. That is the coupling strength or the charge of lepton, I call it lepton charge, is almost as weak as the gravitational charge. When I say as weak, I mean
it looks like we're 2 minutes past 7 o'clock.
Yeah, so compare the strength is the same order as gravitational force. But we are able to use the fact that people estimate the dark matter will be 5 times or 30 times of the observed mass in the universe. If we use this to estimate, we can find out that indeed for a lepton charge, it is weak, but it could be there to produce the observed rotation curve. And last thing I want to do is that once this exists, then it will affect the measurement of the gravitational constant. And what is interesting, because even though we have very precise measurement in the past decade, the final results are not consistent. And people suspect there must be some kind of unknown system error in this experiment. Yeah, okay. These are the kind of things I'm doing recently.